Devastation as homes disappear in Florida.
It ate vehicles and boats and personal belongings. It just kept growing.
A tragic collapse in Oakland, California.
I instantly knew this was the biggest disaster I'd ever seen.
In Washington state, a revolutionary bridge becomes an epic disaster. And in the Netherlands, a cutting-edge design comes crashing down.
The top floor collapsed first, and then the second and the first.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. Sometimes in big builds, there's a delicate balance between man-made and Mother Nature. Get it wrong, and the results can be catastrophic. Like this disaster that struck a suburban paradise in western Florida.
These homes simply disappeared right in front of people's eyes.
This is obviously a huge catastrophe, an engineering nightmare.
And left a community wondering, when will this happen again?
Before you buy a house in Florida, this is something you definitely need to know about.
It was the most devastating thing I think I've ever seen in my life.
Florida, the Sunshine State, boasts the longest coastline in America's lower 48 states. But it's also one of the lowest lying and home to over 30,000 lakes. Hundreds located in the Tampa suburb, aptly named Land O'Lakes.
With year-round sunshine, endless lakes, and beautiful waterfront homes, Land O'Lakes is considered to be one of the top places to live in the whole of Florida.
Originally a group of small towns surrounded by swampland, the name Land O'Lakes was first coined in 1949, and its popularity and size soon grew.
The area's population has quadrupled since 1990, from just under 8,000 to over 35,000.
Most moved here for one reason, a dream home with a waterfront location. Realtor Christy Zimmer knows the local property market well.
It's a wonderful community to live in. It's interesting with property values in this area. We value the properties and how much waterfront they have.
To feed demand for lakeside homes, waterfront development boomed.
In the last 50 years, Land O'Lakes has gone from 350 homes to nearly 6,500. And it appears that not all of them were built on solid foundations.
On July the 14th, 2017, the residents of Ocean Pines Drive were woken by a rumbling. Christy was here visiting a friend.
It was early in the morning, probably about 8 a.m. We were able to sit in the driveway and watch the entire process take place.
A major sinkhole was opening up directly underneath residents.
You could feel the ground underneath you rumbling and just shaking, and I cannot begin to explain the feeling of the ground caving in underneath you, even from that distance. And watching these homes fall into that hole as it ate vehicles and boats and personal belongings with no regard. It just kept growing.
This sinkhole was so massive, it swallowed up 2 homes, a boat, cars, and it just kept on growing. By the time it stopped, it was about the size of 4 Olympic swimming pools.
And to see the kids' toys floating in the top of the water was just heart-wrenching, knowing that they were going to come home to nothing.
That's just on the surface. It was about 50 feet deep to the bottom, which is about 8 times deeper than any of those pools.
It was the most devastating thing I think I've ever seen in my life.
For many who thought they had their dream home, this was the stuff of nightmares. Local reporter Evan Donovan covered the story.
This particular sinkhole uncovered a lot of issues for nearby homeowners that they had no idea about. Your quaint retirement life on a nice little lake in the middle of Florida suddenly getting swallowed up by the ground.
With 2 homes entirely swallowed up, 6 more condemned, and the width approaching 80 meters, the obvious question was what had caused the massive sinkhole to open up. One clear suspect was the area's geology.
Statistically, Florida has more sinkholes than any other state in the U.S. In fact, the area around the Land O'Lakes is known as Sinkhole Alley.
Florida is especially prone to sinkholes because it's largely built on limestone, which dissolves in water slowly, but it always dissolves.
And that slow but inevitable process is the reason there are so many lakes here. Geologist David Wilshaw explains.
The limestone here is very porous, lots of caverns in that limestone, and these circular lakes that we see all around us here are reflections of the ground collapsing into the limestone and creating these depressions in the land surface, which then fill with water and create the beautiful lakes we have in Land of Lakes.
While the sinkholes are actually responsible for the lakes that give the area its unique appeal, they also put its residents at serious risk.
You could say a sinkhole is like an hourglass, with material being eroded from below. Eventually, as the material slips through the cracks, there's nothing solid holding the building up, and the ground gives way with a sudden and dramatic collapse. Since 2003, there have been more than 300 reports of sinkhole activity in or around Land of Lakes. It isn't the Land of Lakes, it's the land of sinkholes.
So, sinkholes are known and expected here. And yet, despite all the evidence pointing to limestone eroding beneath the surface, geologists found that this sinkhole was the result of human activity.
Sinkholes are no surprise to this area, but here it seems that Mother Nature's not wholly to blame.
While sinkholes occur naturally in Florida, geologists believe many, like this one, are man-made. By rapidly developing the area, groundwater is extracted and used for irrigation or residential taps, creating a cavity, destabilizing the ground below. Building work above ground can weaken the limestone even further, causing the soil above the cavity to collapse suddenly and without warning. This type of sinkhole is known as a cover collapse.
The developer decided to dredge the canals to interconnect all the lakes to create more potential waterfront home sites. When they dredged those canals, they filled in areas that probably should not have been filled in at that time. And over time, Mother Nature's just decided to take her property back and turn it back into the lake.
The result? Decades later, the giant sinkhole opens up in Ocean Pines Drive. With homes and a road destroyed, engineers looked at ways to fix it. One solution used elsewhere is to simply fill the hole with a concrete plug. But here, with the land already unpredictable, completely filling it with heavy concrete wasn't viable.
There's no way this land could be used for development again. But to try to prevent it eroding further, engineers stabilized the bottom of the hole with tons of rock.
For now, the sinkhole isn't going anywhere, but it's a frightening reminder for everyone of the danger lurking beneath their feet. Journalist Evan Donovan covered the story.
It is bad luck, it is nature, but it seems like we have the technology now to figure out where it's most likely that these things would pop up, and then what we can do to sort of mitigate the impact when they do happen.
A lot of these homes were built in the 70s and 80s, Today, developers have new tools to check what's underneath, so in theory, this kind of collapse should be a thing of the past.
Geologist David Wilshaw thinks they may have found the answer: ground-penetrating radar.
And I know it looks like a glorified lawnmower, but it's a $30,000 very sophisticated-looking lawnmower. So, we use it all the time here in Florida to image the ground to try and find sinkholes. It puts electromagnetic energy into the ground, which passes through the different soil types at different speeds. And we can tell where those soil types have been disturbed. For example, if we have a sinkhole that might be forming, you'd expect to see those layers of soil dipping inwards towards a sinkhole.
While this technology can help prevent a future disaster, the demand for groundwater and land resources in Land O'Lakes continues to increase. And when you're building on shaky ground, there's always a risk. But despite the threat of other sinkholes opening up, there will always be a demand for homes with a lake view.
Losing your home is heartbreaking, but thankfully this time, no one was hurt or killed.
Pushing the limits in engineering leads to bold innovations and daring new designs. But get it wrong and the consequences can be deadly. Like this highway in California and an engineering catastrophe on an epic scale.
I instantly knew this was the biggest disaster I'd ever seen. It was like a giant had come and toppled the whole thing.
A heartbreaking tragedy that shook an entire city.
The sheer magnitude of this catastrophe turned thousands of tons of concrete and steel into rubble in just seconds.
Many were left wondering why this one structure was so completely destroyed.
I was looking at hand of God type of stuff here.
The San Francisco Bay is home to around 7 million people, drawn by its stunning, rugged landscape.
The Bay Area is one of the most beautiful locations in the world, but it's also one of the most earthquake-prone places on the planet.
The San Andreas Fault might be world famous, but it's not the only dangerous ground beneath this part of California. There are 7 significant fault lines underneath the Bay Area, with hundreds of buildings sitting directly on top of them.
In 1906, San Francisco got a big wake-up call when the largest earthquake in living history struck the Bay Area. The minute-long quake measured a massive 7.9 in magnitude, killed 3,000 people, sparked 3 days of fires, and left the bulk of the city homeless.
San Francisco was all but destroyed. People were scared. Rebuilding would take years. 200,000 refugees left the city. Many moved east across the bay to Oakland, doubling the city's population.
Despite the danger lurking beneath, in the mid-20th century the population boomed. In the 1950s, to ease congestion, construction began on a new section of freeway running through downtown Oakland. To bypass local streets, planners turned to an age-old solution. Instead of going around, they would go over.
Elevated roads have been around since Roman times and are known as viaducts. They're essentially a bridge or a sequence of bridges designed to carry a road over an obstacle, which could be a valley, a marsh, or a busy urban area.
But this would be no ordinary viaduct. The plan was to build California's first ever double-decker freeway. Essentially one long line of bridges standing on top of another, running for more than 3 kilometers. The result? The Cypress Street Viaduct.
In the 1950s, when the Cypress Street Viaduct was built, single-deck roadways were common, but building a double-deck viaduct was a first for California.
Like all structures in the Bay Area, earthquake resistance was a key factor in this groundbreaking design. Structural engineer Jack Moll explains.
The Cypress Street Viaduct was one of the very earliest examples in the United States using pre-stressed concrete, a form of construction where the concrete is cast with the steel reinforcement pre-tensioned inside the structure.
A lot of structures use concrete poured over steel bars or rebar to give it strength. Engineers can make the concrete even stronger by stretching the bars tight before the concrete is poured. When it hardens, the steel is released, essentially compressing and strengthening the concrete. That's known as pre-stressed concrete. It's widely used today, but back then, it was untested.
That was a very new, young technology. In fact, it was perhaps the first bridge in the United States that was built and designed with that technology. They were concerned that if the structure moved, it would develop internal forces that would cause cracking and decrease its service life. And so what was done was to build a structure that was very loosely tied together so it could move.
A fundamental element of this ability to move is steel rods embedded in the concrete where the columns meet, known as shear keys.
Shear keys are designed to allow a building to shake during an earthquake without moving too far. At least that's the idea.
In the viaduct, these were metal rods beneath the upper and lower columns designed to stop the top being shaken off.
Here, to absorb earthquake forces, they would allow some movement, but not so much that the top columns could slide off the bottom. The Cypress Street Viaduct opened in June 1957 at a cost of $9 million and was a huge success. It carried tens of thousands of vehicles a day for the next 3 decades. On Tuesday, October the 17th, 1989, Game 3 of the World Series between the Oakland A's and the San Francisco Giants saw more than 60,000 fans fill Candlestick Park. Anthony Moore, then a Cub reporter, covered the game.
So I went down to Candlestick Park in San Francisco to cover fans outside the stadium who didn't have tickets but still tailgated the game. We had barely gotten equipment out. The camera was just on the shoulder of the photographer when, boom.
Oh my God, we're having an earthquake. Wait a minute. Hold on. 911. Yeah, this is an emergency in San Francisco. What happened? There's a hell of an earthquake, and we've got...
Just after 5 p.m., 60 million baseball fans saw their TV screens go black.
And we've got windows and everything.
The largest earthquake in 80 years ripped through the Bay Area, registering 7.1 on the Richter scale.
The epicenter was over 60 miles or about 100 kilometers away, and the quake only lasted for 15 seconds, but it sent shockwaves that would leave a tragic mark on the city.
A 1.2-kilometer stretch of the double-deck Cypress Street Viaduct had collapsed.
I instantly knew this was the biggest disaster I'd ever seen. It was shocking. It was almost impossible to communicate visually or in words the scale of this devastation.
Mark Hoffman, then a lieutenant with the Oakland Fire Department, was on duty nearby when he realized a major disaster was unfolding.
We're only 2 blocks away from 14th and Broadway. That's basically the heart of downtown. When we pulled up here on 14th, I looked to the right. I saw a giant plume of smoke. Told the driver we're making a right.
From here on out to about a mile and a half, the freeway was either partially or completely collapsed.
About 25 feet up was the first deck, and then the upper deck had collapsed, pancaked onto the first deck. We were roughly located where it was intact all the way to right about there, and then was collapsed from then on, as far as the eye could see.
107 vehicles were on the Cypress Street Viaduct as it collapsed. Rescue crews and local residents worked to free people trapped in the rubble.
We had an elevated ladder that we were able to throw, got us up onto the lower deck, but on top of the collapse, and we went to work.
The rescue mission ran through the night, but despite the city's best efforts, 42 people lost their lives. In the coming days, questions were asked. When so many structures escaped serious damage, why was Oakland's Cypress Street Viaduct so catastrophically destroyed? After the collapse, investigations suggested that the pioneering use of pre-stressed concrete during construction 3 decades earlier had played a key role. Engineer Jack Moll explains.
We didn't at that time understand very well how big the earthquake forces could be in a structure of this type. So the amount of steel that was built into it was very little. So when the earthquake came along, the loose structure moved a lot. Those parts of the concrete that were inadequately protected by steel, they crumbled. As they crumbled, they lost the ability to support the weight of the structure. It started to come down, and as it moved downward, it broke other pieces of the structure, and the collapse projected along the length.
As the viaduct shook during the earthquake, the shear keys connecting the columns began to vibrate, cracking the concrete surrounding them.
Without proper support, they broke sideways through the columns. The structure collapsed.
So, the pre-stressed concrete surrounding the shear keys simply wasn't strong enough, and this wasn't catastrophic for just one section of the viaduct.
With a structure of this type, if during an earthquake, one of the elements should fail, in this case, one of the columns supporting the bridge deck, there's the potential that it loses its support, and as it begins to fall, it starts taking down the entire rest of the structure. In the case of the Cypress Street Viaduct, some very vulnerable pieces of the bridge failed first, and then as the structure began to fall, it, like a set of dominoes, took down the rest of the structure along the length.
Engineers may have overestimated the strength of the concrete, but that alone didn't explain the carnage. The disaster was made so much worse by the local geology. Earthquake engineer Jonathan Bray explains.
So the Cypress structure itself is actually founded on dense sands and stiff materials, but then it goes out across an old mudflat that has been covered with some artificial fill. And that mud in that location is anywhere from 3 to 7 meters thick. It's soft, it's weak, and that's the part of the Cypress structure foundation that shook the most violently during the earthquake.
The solid rock helped to dampen out the vibrations, but by contrast, this soft bay mud helped to amplify the vibrations by as much as 5 times. This quirk of geology made things much worse.
The effect of these huge amplification forces hadn't been factored into the original design.
When the ground comes and shakes a building, you can see that this shaking level, this period of the shaking, really causes this one to accelerate while the other ones barely move. If I shake it a little bit slower, you can see that there's very little shaking of the lower masses, but that longer mass, which is softer, tends to get amplified the greatest. When you build a structure on top of a soil deposit that amplifies shaking, you have an amplification of the forces that are placed on that structure, and therefore it causes more damage.
This combination of structural weakness and the soft geology proved to be fatal. After the disaster, the Cypress Street Viaduct was demolished and the freeway was relocated to the west along the old Southern Pacific Railroad corridor. Lessons were learned, and instead of a double-deck viaduct, engineers built a single-level bypass.
The failure of the Cypress Viaduct was one of those failures that taught us what we needed to do differently in bridge design.
One key lesson learned from the collapse was the need for a significant increase in the amount of steel used to reinforce concrete.
Typically, when we build reinforced concrete construction today, we've got very heavy amounts of binding steel that hold the concrete together, so that when an earthquake overwhelms the structure, if there's local crushing of the concrete, the reinforcement inside will hold it together and prevent a repeat of the Cypress Street Viaduct collapse.
These new breakthroughs in engineering and technology will hopefully make all structures safer in an earthquake, in the hope that something like Cypress Street can never happen again.
Cypress Street was renamed Mandela Parkway, and the Cypress Freeway Memorial at its heart is a poignant reminder for future generations of this tragedy.
In terms of total loss of life, in terms of damage to the infrastructure of the community, how long it took to rebound, what it just showed everyone in terms of potential, this, I think, was worst case.
With big structures, engineers aim high and push the boundaries with ambitious designs. But push too far and it can be a recipe for disaster. Washington State has been victim to this mistake in a very big way.
This has to be one of the most famous bridge collapses of all time.
This catastrophic failure earned its place in the Engineering Hall of Fame for all the wrong reasons.
We were seeing great chunks of concrete fall off the bridge.
With so much carnage, it seems incredible that no one was killed.
Washington State is a wild landscape shaped by powerful forces.
The Pacific Northwest has a very rugged feel from the mountains to the jagged coast. With waterways threading through the land, it's long been a haven for bridge engineers.
More than half a century ago, one crossing over the Tacoma Narrows revolutionized life for residents. Dale Wersing has lived here since the 1930s.
Before the first Narrows Bridge was built, the only reasonable way from Tacoma to Gig Harbor was to take a ferry. Your alternative was a long drive, so people in Tacoma were very excited about this improvement in their lives.
With their deep, steep sides, the 1.5-kilometer wide Narrows have long been a challenge for bridge engineers. These twin suspension bridges have stood here since 1950 and 2007. But their now infamous predecessor lasted barely 4 months after opening. The original Tacoma Narrows Bridge took almost 2 years to build. Its giant towers loomed 135 meters over the Narrows, while 600 kilometers of cables held the road deck in place.
When the Tacoma Narrows was built, it was the third longest suspension bridge in the world. Only the George Washington and Golden Gate bridges were longer.
The Tacoma Narrows Bridge might not have been the world's longest, but in engineering and design, it was way ahead of its time. Engineer Stephen Ressler explains.
Early in the 20th century, suspension bridge design underwent a kind of a revolution as a result of a radical new mathematical theory of suspension bridge analysis. Long-span bridges could be designed such that they were much more slender, much more elegant.
That streamlined, elegant effect was achieved by drastically reducing the side profile of the bridge.
Most suspension bridges back then supported the road deck with lattice beam trusses, which let the wind flow through. Here, to slimline the bridge, they used narrower, solid girders.
Using solid girders instead of a lattice structure allowed engineers to reduce the depth of the girders from around 9 meters to just over 2. Instead of through, the wind would pass over and under, and yet, crucially, the bridge would be just as structurally sound. At least that was the theory. The lead engineer claimed the Tacoma Narrows crossing was the most beautiful bridge in the world.
The bridge engineers achieved their dream of a slim, elegant structure, but there were signs of trouble. Even before the bridge opened to traffic, it was known to rock, even in gentle winds, earning it the nickname Galloping Gertie.
The bridge wasn't just swaying, it was twisting and bouncing.
Engineers tried various fixes from extra cables to dampers, but nothing would stop the swaying.
It seems hard to believe, but although the bridge did clearly move, it was deemed safe for use and opened on July the 1st, 1940. Dale was just 4 years old at the time.
One of my memories from my childhood is going for a walk on the newly built bridge, and I have a recollection of the bridge kind of undulating, moving in waves.
On November the 7th, just 4 months after opening, the wind seemed to be making Gertie gallop more than ever.
There were 3 people on the bridge when the buckling started. The bridge was twisting and jumping so violently it was impossible to stand up, so they had to crawl to safety.
The movement of the bridge quickly worsened, to the point at which the cables could no longer handle the load. Just over an hour after the rocking started, the central span dramatically collapsed, leaving little more than the main towers standing.
As I watched Galloping Gertie fall, we were seeing great chunks of concrete fall off the bridge and splash into the Narrows.
Thankfully, everyone made it off the bridge before the deck failed. The only victim was a dog named Tubby, who was trapped in a car. In the aftermath, an investigation was launched to determine exactly what had gone wrong. To prevent a repeat, engineers needed to know why Galloping Gertie had collapsed so dramatically. This included wind tunnel tests, which revealed that the failure was connected to the cutting-edge slimline design.
The heart of the problem was the solid supporting girders. They were interacting in an unexpected way with the wind passing over the bridge.
Engineer Stephen Ressler explains.
What happened with the Tacoma Narrows Bridge, and is a common phenomenon on long, flexible suspension bridges, is that the wind blowing across the bridge causes aerodynamic effects, which result in periodic vibrations of the bridge. If I disturb this structure, it will vibrate at a certain frequency, that is, a number of cycles per second. The aerodynamic phenomenon that occurred on the Tacoma Narrows Bridge was that the distortion of the bridge under the action of the wind blowing across it caused the disturbance. That disturbance generated turbulence in the wake of the wind flowing across the bridge, and that turbulence reinforced the deformations, such that with each cycle, the aerodynamic effect of the wind blowing across the structure reinforced the size of the individual vibrations. So the vibrations simply got larger and larger and larger.
The phenomenon behind these self-sustaining and destructive vibrations was little known back then. Today, it's called aeroelastic flutter.
Aeroelastic flutter is a very complicated phenomenon, but fundamentally, if the natural vibrations of the structure and the wind work together, the flutter can get so bad that the structure shakes itself apart. And that's what happened with the Tacoma Narrows Bridge.
Learning from the collapse, engineers designed a new bridge. This time, they were taking no chances.
The solution was really just to revert back to the technological form that was prevalent prior to the design of this structure. And that was simply the use of robust stiffening trusses to stiffen the deck of the bridge. And so just as that stiffening truss was the solution to the problem of handling heavy concentrated loads, it also proved to be an entirely effective solution to the problem of wind-induced vibrations.
Engineers were able to repurpose the approach span from the original slimline structure, with the difference in depth between the old and new technology blindingly obvious. Project manager Tim Moore explains.
What you're seeing here are 3 of the original Galloping Gertie 1940 bridge spans. These spans were not damaged in the 1940s collapse. What's unique is when we get to the side span, you can see the 43-foot deep stiffening truss. It's torsionally significantly stiffer than the plate girder system of the 1940s Galloping Gertie bridge.
The new reinforced Tacoma Narrows crossing has carried traffic since October 1950 without the slightest hint of a gallop. It even earned the nickname Sturdy Gertie and can withstand wind speeds far in excess of those that brought down its predecessor.
On the 1940s bridge, the flutter speed has been determined through wind tunnel testing to be a speed of around 20 to 30 miles an hour. The 1950s bridge has a flutter speed that exceeds 127 miles an hour. We don't ever expect to see those kinds of winds, and therefore the structures will remain stable for their entire existence.
Over time, traffic using the crossing became so high that in 2007, a twin suspension bridge was opened, running next to Sturdy Gertie.
This disaster highlighted the risks of pushing the boundaries with massive structures and has influenced bridge designers ever since.
Sometimes in engineering, even the best laid plans can go disastrously wrong, and the smallest mistake can lead to catastrophe. Like this pioneering structure in the Netherlands, which failed spectacularly.
The top floor collapsed first, and then goes the third floor, and then the second and the first.
A building reduced to rubble in seconds.
The mistakes hidden within every level of this build triggered a nationwide panic.
The Dutch have a long history of exploration, and it feeds into all walks of life, including their architecture and engineering. Local journalist Yuwar Abbas explains.
Dutch engineers, they like to build fancy structures, not only for living, let's say, to use it, but also to make it look nice.
This is the Hourglass building in Amsterdam's Zuidas business district.
This building is a great example of Dutch innovation. When it's complete, it will house offices and a hotel, all in a cutting-edge geometric design.
But this development isn't only about the aesthetic. It's being constructed using a pioneering new technique. Instead of using standard concrete for each floor of the building, engineers have opted for biaxial voided slabs.
Biaxial voided slabs sound very technical and complex. However, the principle of this technique is relatively simple, not to mention ingenious.
When constructing a new floor slab, rubber spheres filled with air are placed into a steel framework. Then concrete is poured into that framework. The result is a slab that uses 1/3 less concrete than a solid slab.
Less concrete means that the floor slab is significantly lighter and cheaper, but it is just as strong as a solid concrete slab.
Structural engineer Professor Robert Nies is familiar with the technique.
It's a very good practical thing, because you have to reduce the weight of the floor. All this stupid concrete, which is enormously in weight, 2.5 times as much as water. So it's all pressing down all the time long. So if you can make that into air, you save enormously weight of the structure. So it's a very clever system.
With this technique, architects can create bigger spans in buildings requiring uninterrupted space.
It's an ideal method for buildings with open plan spaces, like an indoor stadium or a car park.
In 2016, architects working on Eindhoven Airport were planning to use air-filled concrete in a new, state-of-the-art car park.
This is the second largest airport of the Netherlands. This demands extra space for the parking. So the parking garage here is located perfectly near the Eindhoven airport. And for technology like bubble deck, this is the perfect application because you have wider floors and you want to use your space efficiently. Moreover, this gives you an advantage of sustainability.
In late May 2018, with the building nearing completion, disaster struck. A large section of the car park collapsed.
On the day of the incident, it was a complete chaos here. 4 floors of this building behind me collapsed. The top floor collapsed first, and then goes the 3rd floor, and then the 2nd and the 1st. And people were shocked. The biggest fear of the people were, are there any casualties?
Luckily, no one was hurt. But just hours before, dozens of workers had been on site. An investigation was launched to discover what was behind this catastrophic fail. All eyes focused on the biaxial voided slabs.
The section of floor that had caused the collapse was construction of the bubble-filled concrete. But it wasn't the slabs themselves that were to blame. It was how they were laid.
Engineers were positioning the slabs to span a large space between 2 main structural columns. But instead of following the plans that had each end of the slabs placed on the supporting columns, they rotated them through 90 degrees. So some slabs had no actual support from beneath. This created a weak, unsupported point in the middle. The investigation concluded that the decision to rotate the bubble-filled concrete slabs by just a quarter turn was the crucial mistake.
Normally, these plates are made in long plates, and they are spanning from wall to wall. In this case, they decided to use it the other way, to make plates like this and in between like this. This can work, but it means that where the joints are, has to be extra reinforcement. They forget it.
This is such a simple fail. If the plans had been followed correctly, the floor would have been fine.
The report found that without reinforcement, the floor was so vulnerable that even the slightest increase in load was enough to cause it to buckle.
When this car park behind me collapsed, this was big news in the Netherlands because most of these government buildings and schools in the Netherlands use the same building techniques as was used in this car park. They pinpoint 150 buildings which required investigation, thorough investigation.
To prevent another catastrophe, the Dutch Safety Board inspected the buildings in question to ensure that the bubble-filled concrete had been installed correctly.
Until the investigation was finished in these 150 buildings, the people and employees in those buildings were instructed to be careful. For example, they were not allowed to gather in numbers. They were not allowed to dance.
It sounds ridiculous to ban dancing and office gatherings, but this reveals how worried people and organisations were about the structural integrity of these buildings.
All the buildings investigated received the all clear, and the restrictions imposed on employees were lifted.
I've no idea how much dancing typically goes on in Dutch government buildings, but now it's official, you can bust your moves without fear of causing a building collapse.
Not only that, but the use of bubble-filled concrete is more popular than ever across the Netherlands.